All right. Hi, everybody. Welcome to our Closer Look Journal Club for today. My name is Matt Bursey. I'm an assistant professor at Washington University in St. Louis, and I have the privilege of hosting today with my colleagues Manuel Rausch at University of Texas at Austin, Emma Lejeune at Boston University, Johannes Weckemeyer at Stevens Institute of Technology, and Adrian Buganza-Tepele at Purdue University. If this is your first time at one of these Journal Club meetings, welcome, and we're glad that you're here. And if this is not, and you've been here before, welcome back. And we're also glad that you're here. Basically, the goal of this Journal Club, whenever it was established, was to bring together experts in the field of biomechanics and mechanobiology, and sort of present some of their current and ongoing work to trainees and current professors in the field. And so we're excited that this is now the second year of this. And if you've seen the list of presenters for this semester, you can maybe appreciate that we have people from various fields and disciplines across that biomechanics and mechanobiology spectrum. With this semester of talks, we've sort of asked the presenters to give shorter form presentations, to give extra time for discussions after the talk itself. And so those of you on the call today, I would just sort of encourage you to identify potential questions that you may have for the speaker, and don't be shy to bring those up in the discussion afterwards. So with that, I'm delighted to introduce our speaker for today, Professor Chiara Bellini from Northeastern University. Chiara has her bachelor's, or she received her bachelor's and master's degrees from Politecnico di Milano, pronounced very poorly, but Politecnico di Milano. She got her PhD from the University of Calgary under the supervision of Professor Elena DiMartino. And then she did her postdoctoral work at Yale University in the lab of Jay Humphrey. After that, she moved on to her current position at Northeastern as an assistant professor in the bioengineering department there. And her research is focused on cell-mediated growth and remodeling processes in diseases of the cardiovascular system. Today, we sort of asked her to present a recent publication from her lab that's called, or that's sort of titled, The Structural and Functional Remodeling of the Female ApoE Null Mouse Aorta Due to Chronic Cigarette Smoke Exposure. So with that, I will yield the floor, and we're excited to hear what you have to say.
Thank you, Matt, so much for the introduction, and thank you to all the organizers for inviting me here. It's really nice to see everybody, even though just virtually after the past couple of years. So let's just that right in. Let me see. All right, I may have, sorry about that. I was in the wrong slide. Here you go. Okay, so as we all know, cardiovascular disease is a leading cause of death, especially amongst adults 65 years and older. And advanced age is a primary risk factor for cardiovascular morbidity and mortality. So the natural aging process interacts with factors such as elevated body mass index, elevated blood pressure, elevated cholesterol, and smoking, which is the topic of his talk, to increase the risk of acute cardiovascular events, including myocardial infarction, ischemic stroke, and heart failure. So this relationship between cardiovascular health and mortality supports the existence of a dialogue between aging and cardiovascular disease. So on one side, age-related changes in the structure and function of the heart and blood vessel alter the environment where pathophysiological processes occur. And so, for example, they may influence the threshold for disease initiation or disease progression or the severity of symptoms. Then on the other side, pathological processes may modify the natural course of the aging process and may, for example, induce an organism-wide accelerated decay. So I think that this notion is really crucial to interpret the outcomes of treatment that last a considerable portion of an organism lifespan, like the one that we will discuss later today. So as I was reflecting on this idea, I came across this recent paper that reviewed upward of 300 published articles to identify the chemical and non-chemical stressor for childhood obesity, which is a well-known risk factor for cardiovascular disease later in life. So of course, there are socio-economical and demographical aspects that contributes to this equation. But what was surprising to me is that stressors such as indoor and outdoor air quality, exposure to aerosol from tobacco products, and even doctor-prescribed medication influence the risk of developing obesity and therefore cardiovascular disease later in life more than other well-recognized factors such as diet and exercise. And so as life expectancy continues to rise, I really believe that us, the scientific community, should devote effort and address this concern and trying to study potential sources of cardiovascular toxicity that are likely to cause downstream events later in life. And so with this in mind, my lab set off to study the effects of chronic cigarette smoking. So I always like to give an historical perspective to research questions. So here you go for cigarette smoke. So mass production of cigarettes began in the 1880s when the first cigarette making machines were developed. And so you have an increased production of cigarettes and then cheaper prices. And that acted as an incentive for tobacco companies to actually increase consumption. And so by the end of the 19th century, magazine carried advertisement for cigarette from different tobacco company, like the one that you see on the top left. So upon a request of President Kennedy, the Surgeon General published the first report on cigarette smoking in 1964, and it has been regularly updated ever since. And the last update was published in 2014. So over the past now 57 years, we learned that cigarettes are the leading cause of preventable premature death. Smoking is associated with a huge annual financial burden, both in terms of healthcare cost and loss of productivity. Smoking diminishes the overall health perception independent of sex. And finally, thus far, sufficient evidence has been collected to link smoking to AAA, abdominal aortic aneurysm, atherosclerosis, coronary artery disease, and stroke. So why are we still studying cigarette smoke? And I think there are two answers for this. So the first one is that the physiological and molecular mechanism by which cigarette smoking causes cardiovascular disease are not really fully understood. And we're not expecting the number of people that currently smoke to really go down in the next future. It has leveled off over the past few years. And second, cigarette smokes or the effect of cigarettes smoke are the baseline to which we can compare the effects of electronic cigarette vaping. So electronic cigarettes have been introduced in the US market in 2007 as smoking cessation aids. But really oftentimes people end up both smoking and vaping, a population that's called dual users. And furthermore, e-cigarettes have renormalized smoking in young adolescents and adults. So the first Surgeon General report on vaping has been published in 2016. It is worth noting that most e-cigarette companies are owned or have been acquired by tobacco companies, including the very popular Juul. So there's an interesting study from Stanford that really shows how advertisement for e-cigarette is heavily influenced and is really drawing inspiration from cigarette advertisement for 50 years ago. And so naturally we wonder, are we repeating history? It's tricky because epidemiological data on the health outcomes of chronic vaping are not available, and they will likely take decades to collect. So we must rely on animal model of aerosol exposures to collect scientific evidence for regulatory purposes. And so in my lab, we chose to use epoenol mice to generate a mouse model of chronic cigarette smoking. So apolipoprotein E is a ligand for lipoprotein receptors that are involved in lipoprotein recognition and clearance. And so the lesion of this gene causes mice to develop severely elevated lipid and cholesterol profiles. And this lipidic imbalance makes ApoE mice prone to develop both atherosclerosis and airway remodeling. And so using these mice really gave us the opportunity to study the cardiovascular and respiratory comorbidities that often are seen in smokers. So we started off by creating or developing a framework to expose mice to cigarette smoke. I have a video here, hopefully it's gonna play. So we use a system that it's called InExpose. Here we go. From Cyrec to generate and deliver the smoke. And so in this system, the cigarettes are held into a smoking robot. It's a carousel, contains up to 24 cigarettes. They rotate, they get lit, and then there is a pump, which has a red sticker here that takes the puff and then delivers it to an homogenization chamber, the one in green down here that mixes it with air. And then there is a second pump in blue that then delivers the aerosols to the mice that are located here on what we call the nose-only exposure tower, where the mice are held in soft restraint so that they can breathe. So we also use this same setup to characterize the smoke. Cigarette smoke is a complex aerosols that contains both solid particle and liquid droplets that are suspended in air. It includes thousands of chemicals, and approximately 100 of them are recognized as harmful or potentially harmful. And the particles themselves in the smokes are generated from the high temperature processes that occurs during combustion. So we are particularly interested in particle mass and size, number concentration, as well as carbon monoxide concentration, because these are two of the 6 criteria pollutants that are identified in the Clean Air Act by the Environmental Protection Agency, or EPA. And why is that? So fine and ultrafine particles less than 2.5 micron in diameter are particularly dangerous, as they penetrate deep into the lungs and are more likely to cause a biological response. So we collected particle data with 2 particle sizers from TSI, OPS, that's based on optical mobility for larger particles, and EPS, which is based on electrical mobility for smaller particles. And we use that to generate these heat map, dynamic heat map of particle size, number, concentration in cigarette smoke. So let me get you through these heat map. On the x-axis, we have the time that it takes to smoke a cigarette, approximately 7 minutes. And on the y-axis, we have the size channels of our instruments in a log scale. And of course, the color indicates the concentration. So we really like this representation because it makes it easier to compare puffs. And you can see at the beginning, the puff is starting to ramp up to a steady state that is then maintained for the rest of the exposure. We can then integrate all this information over time and generate a distribution of particle size, number, concentration, which is the one on the right. And we saw that that distribution is well enveloped by a log normal function with mean parameters that are set to the count median diameter measured experimentally, and the dispersion parameter for the log normal distribution set to the geometric standard deviation, which is calculated also experimentally, and it's called GSD. So this analysis essentially confirms that cigarette smoke contains particles that are smaller than 2.5 micron, which are expected to cause damage. So next, we sought to identify a biomarker of cigarette smoke exposure. So nicotine is quickly metabolized on the order of minutes. And so we measure plasma concentration of cotinine, which is a nicotine metabolite, following inhalation of cigarette smoke from 8, 16, 20, and 24 cigarettes. We eventually decided to treat the mice with the smokes of 16 cigarettes per day, which elicits a cumulative cotinine concentration of approximately 71 nanogram per milliliter, which is similar to what has been reported for smokers. So because we are interested in the long-term effects of smoking, we exposed mice 5 days a week for 24 weeks using air as control. And we monitor their weight and blood pressure each week, but quantified circulating inflammatory cytokines, tested vascular function, and evaluated the atherosclerotic burden at endpoint. So let's move on to the results. And so throughout the 24 weeks of treatment, blood pressure in the air control groups, which are the gray square here, fluctuates around baseline with an average systolic value of approximately 110 millimeters of mercury. On the other side, cigarette-exposed mice experience a linear increase in systolic blood pressure within the first 11 weeks of exposures. And then after that, it stabilizes around an average value of 134 millimeters of mercury. And so these observations recapitulate occurrences in chronic smokers, and I put a little man there. So it should be a female. I forgot to change it. These mice were female, but so whenever you see that icon close to a measurement, it means that our findings are consistent with observations in human. So because aortic thickening is a well-established adaptive response to even mild hypertension, we measure thickness of the aorta at 4 anatomical locations. So the ascending between the heart and the left and the right subclavian artery, then the descending between the left subclavian artery and the diaphragm, the suprarenal between the diaphragm and the renal artery, and the infrarenal between the right renal artery and the iliac bifurcation. So I will use this nomenclature throughout the talk, though we will then focus on only the suprarenal. So as expected, the aortic wall is thicker in all regions, with the ascending aorta once again mimicking the intima media thickening that is reported in the carotid artery of smokers. So to better understand the source of wall thickening, I kept asking this question to my students: where does the thickening come from? And so we stain tissue cross-section with Picosero's red, which help visualizing collagen. So at all anatomical location except for the ascending, and we'll come back to this later, exposure to cigarette smoke clearly increases collagen content in the adventitia, which is the outermost layer of the wall. And so to interpret these microstructural observations in view of the tissue mechanical response, we performed inflation extension tests on the aorta. So I'm going to show here the results for the suprarenal aorta, but all the other regions fairly behave the same and follow the same pattern. So the circumferential stress versus stretch curve for baseline, which are the light triangle, and air exposed, which once again the gray square, are fully overlapped. So this indicates that really not much natural aging has occurred between 8 and 32 weeks of age. However, the circumferential stress versus stretch curve for the cigarette exposed aorta, which is the one in black circles, then extends to the right of the control curve. So as a result of larger systolic pressure in the cigarette group, the circumferential stretch at systole in the cigarette aorta is higher. Nevertheless, the systolic values of stress and intrinsic stiffness of tissue in the circumferential direction remain comparable across groups. So these results are quite intriguing from a mechanobiological perspective because they suggest that collagen deposition that is promoted by cigarette smoking need not cause intrinsic stiffening of aortic tissue. And so to explain this mechanism, we use the mechanical data to estimate the constitutive parameters of the wall, and then we use those parameters in a forward model to predict the mechanical responses. So what you're seeing here are the predicted stress versus stretch curve for the cigarette and air exposed aorta. So the red dot indicates the state of stress in the aortic wall under normal pressure loads, and the red line there visualizes the intrinsic stiffness of tissues. And so due to the gradual increase in blood pressure throughout the first 3 months of exposure, the aorta descends to progressively larger diameters that experiences larger values of stiffness, which are represented here by the blue line. So we speculate that cells may respond to this stiffening by laying down new collagen in this already distended configuration, presumably using normal deposition stretches. So as a result, the collagen in the cigarette exposed aorta engages at larger tissue level stretches, delaying the stiffening of the stress versus stretch curve. And so the net effect of this remodeling process is an overall softer material response in the circumferential direction, which is able to accommodate higher pressure while maintaining circumferential stress and stiffness of the control aorta. And so these material softening upon sustained increase in blood pressure has been both observed experimentally in the thoracic aorta of hypertensive rats, and has also been predicted numerically using a constituent-based model of arterial growth and remodeling. So our data seems to be consistent with that. So despite this tissue softening and the higher pulse pressure, the thicker wall in the aorta of the cigarette exposed mice limited the change in luminal diameter between diastole and systole, which contributed to the decreased distensibility of the artery throughout the cardiac cycle. And so that means that although the intrinsic stiffness of tissue in vivo remains the same, the aorta becomes structurally stiffer because it changes in geometry. So this is important because, again, it brings us back to what has been observed clinically, and there are plenty of reports that indicates the increase in structural stiffness of the aorta in smoker, increase augmentation index, high pulse wave velocity, decreased aortic distensibility or compliance, and that is, by increasing the workload on the heart, is a risk factor for cardiovascular disease. Structural stiffening also occur in the axial direction, where the exposure to cigarette smoke results in a leftward shift of the stress versus stretch response. And so this reduced axial extensibility manifests as a decreased value of the axial pre-stretch, which allows to maintain stress and stiffness within or below physiological level. Since, again, this is also very interesting because we do not expect inhalation of cigarette smoke to influence axial tethering. And so perhaps what's happening is that collagen deposition hinders elastic fiber recoil, reducing the axial pre-stretch. So all this shows that the microstructural remodeling supports circumferential tissue softening when it's combined with larger pressures, but attains the opposite effect on the tissue response to perivascular tethering, which is, again, unlikely affected by cigarette smoking. So finally, larger circumferential deformation compensate for the reduced axial stretch and prevent significant changes in the store elastic energy, at least for the suprarenal aorta, though this parameter decreased significantly in all other regions. So the last piece that we're missing in our analysis is to evaluate the atherosclerotic burden. And so we analyze the size and microstructural composition of the myointima. So as expected, lesions form in the aorta of atherosclerosis prone EPOE mice, whether they had been exposed to cigarette smoke or not. Yet by the time of sacrifice, the concentration of the pro-inflammatory cytokine IL-6 is higher in the blood of cigarette-exposed mice, and the area occupied by the neointima is 40% larger, and we're talking about the ascending thoracic aorta here in the cigarette group compared to control. So also the neointima of cigarette-exposed vessel contains less alpha smooth muscle cell positive cells, which are expected to stabilize the lesions by facilitating the secretion of structural matrix. And further, the exposure to cigarette smoke is associated with a larger percentage of CD68 positive macrophages, which may render the lesion more vulnerable because of the increased proteolytic activity. And so consistent with this, the inhalation of cigarette smoke reduces the thickness of the fibrous cap, which is outlined in red there, and decreases the overall collagen content of the lesion. So taken together, these findings indicate that the atherosclerosis burden is worse in EPOE mice exposed to cigarette smoke, even though their body mass is lower and they were fed a regular fat diet. So this emphasizes the intrinsic effect of smoking on the cardiovascular system. So to briefly summarize, the ultimate goal of this project is, an overarching goal, I should say, is to elucidate the cardiopulmonary outcomes that are associated with the chronic inhalation of aerosols from tobacco products, including conventional and electronic cigarettes. So we confirmed that cigarette smoke contains fine and ultrafine particles that are dangerous to human health. Our methods for exposing mice to cigarette smoke attains cotinine concentrations that are consistent with those detected in smokers. And next, we talked about the results of the mechanical and microstructural analysis of the aorta from EPOE null mice exposed to cigarette smoke for 24 weeks, concluding that our mice well recapitulate occurrences of mild hypertension, aortic thickening, structural stiffening, and worsening of the atherosclerosis burden that are often reported in smokers. In addition, we showed that cigarette smoke does not alter the intrinsic stiffness tissue despite an overall increase in collagen content. And so these really unprecedented data provides the baseline against which we'll then compare the effects of new tobacco products, including e-cigarettes, which we have now collected all the data and we're in the process of analyzing. So I'm going to stop here. I think I used up all my 25 minutes. Before opening the floor to discussion, I would like to acknowledge all the students who have worked on this project, particularly Yasmin, Jackie, and Matt that I saw are on the call. The collaborator in particular, Jessica Oakes and Barbara Rankelawan, and the funding agencies. Thank you all for your attention, and I'd be happy to answer any question you may have.
All right, thanks, Chiara. That was great. Maybe since there's a question in the chat, I'll just maybe read that out and we can start with that as the first question. All right, this is from Nusha Carvason. This is one of my students. She says, Dr. Bellini, what is the ratio of smoke to fresh air that is used to expose the mice, presumably in your system there? And how did you decide this number? How was that ratio chosen?
Great question. So the ratio was, I don't remember the exact value of the ratio, but what was chosen was the average particulate matter that we were giving to the mice. And so we settled on these 550. We were targeting between 500 and 600, and that's what we got exactly in the middle. And that is leveraging literature that already exists. Nobody had really looked at the cardiovascular system, but there has been a lot of literature on rodent exposure to cigarette smoke that looked at the lungs and the inflammation in the lungs. And it seems that that was a good target particulate matter concentration that would that would be able to generate, that we could use to generate a mouse model of chronic cigarette exposure.
I've got a question for you. How did you define the axial pre-stretch?
So, you know, there are different ways to do it. One way could be to put markers before you extract the artery and then take it out and measure the distance between the markers when it's not, when it's in vitro. What we did was to use our biaxial device to figure out what is the value of the axial stretch that maintains the axial force constant within the range of pressures that we're interested in, that we expect to be in vivo. And that is a value that is an energetically favorable length in a sense, because it does not need, the artery does not need waste energy to change the force as the pressure varies throughout the cardiac cycle. It has been shown, I think, Jacopo, I saw it here. So he has seen, compared the two measurement, and 4 vessels that are tightly, are set in a tight position in vivo, such as, for example, the descending thoracic aorta, the superior aorta, and that they don't really change much their length throughout the cardiac cycle. That seems to be a good approximation. For the ascending aorta, of course, it changes length throughout the cardiac cycle. That's a whole different story, but we still like to use that value as a representative value because it's something that allows us to compare the same vessel within different groups at group specific length or stretch that attains the same behavior.
Yeah, that's what I use for defining my pre-stretch too, but I'm wondering if with these diseased tissue, if the physiologic pre-stretch changes with the extra collagen deposition, like do we see the stretch at which we don't have any axial change in stress affected by that extra collagen deposition, and does that increase the power required by the heart to pump blood through there?
Yeah,
so I'd be interested to see if that does change with fiducial markers and looking at the force response to pressure oscillations.
Definitely. So we did see a decrease in the axial stretch, and I do think that that's because of the collagen deposition. And so the idea is that because I do not think that the axial stretch is imposed by perivascular tissues. And so I do not expect those to change because of cigarette smoking. So I expect, as we saw, the pressure to change. And so to compensate in a sense for this increase in pressure without increasing the intrinsic stiffness of tissues in the circumferential direction, one of the disadvantages of that is that it becomes stiffer axially as well.
Great, well, thank you.
Are there any other burning questions from the audience?
Shu-Sung, go ahead.
I actually have a question, but not very related to this study. But as a smoker, I'm very curious. What if the the mice quit smoke? Like, do you have any plan to do this study? And what will do you have any preliminary data for it? Or if not, are you gonna plan some study for this?
Sorry, I think I missed. How do the mice do what?
Quit smoke.
Crave?
Quit. Sorry.
So if they're exposed to smoke, right?
Yes.
And then they stop smoking.
Crave. Okay. Yes, they absolutely do become addicted to nicotine. It's at the end is fairly, and my students here can can attest to that, that it's very easy to put them into the restraint, especially, so we do expose them 5 days a week, and then not on the weekend, and then we start on Monday. And it seems that after that 2 days of not receiving nicotine, they do need the effects somehow.
Interesting. Thank you.
Along those lines, I may just sort of follow up with that. You show that whenever they are given the chronic cigarette exposure, there are these functional and structural changes. Do you expect, or could there be any sort of reverse remodeling if they are taken off of the chronic cigarette exposure for a certain amount of time, or for a long amount of time? Someone who maybe smokes for decades and then stops for many more decades.
Oh, that's definitely one of the long list. It's a question that's one of the long list of questions that we have. What happens when people, or you quit smoking or switch to electronic cigarettes? Does that resolve the compromise that you have created to your system or not? I don't know the answer to that question yet, but it's definitely something that I would like to look at.
So I really like the work that you presented, and I was curious that there's always a slight difference between control and baseline. And even though it's not worth talking about, I'm curious if you have a motivation for people doing mice work, why that would be. Is it an age-related effect? Is it that you're going through your experimental setup has an impact, even though they just inhale air because for whatever reason? Can you elaborate on that a little bit?
So excellent question. I think that there are two aspects here. So the baseline was at 8 weeks, and the control, so they just came from Jackson. They hang out for some times in our vivarium. Then the 32 weeks are the one that have been exposed to air. And so those are the age match. I do think that there is a little effect of aging, and we have been studying the aging, not specifically in these mice, in more of a wild type environment. We do not expect really 6 months to cause a drastic change. I think that you need, for some parameters, even 2 years. And again, I'm calling out on Jacopo here, but even after 2 years, you don't see dramatic change in some parameter that you would expect to. So the other question is, does the exposure to air affect them somehow? I do think that I'm not expecting it. Honestly, they're just chilling in very soft restraint to which they have been used to. So I'm not expecting that to cause dramatic change. There will probably, the first few times that they get in, the blood pressure and heart rate will go up and they will get nervous, but after some times, I think that they're okay with it. So I'm not expecting it.
Yeah, thank you.
Can I ask a quick question that I'm sort of latched onto something you just said, Chiara. We don't study arterial mechanics, but we study skin mechanics, and we use mice as a model. And you just said that even after 2 years, you don't see a lot of the changes that you would expect with aging. And Adrian is on this call, and actually my student who works on this as well. And we've actually been pretty disappointed with mice as a model for aging skin. And so we're very fortunate in that we have access to the National Institute of Aging mouse colony that provides mice up to 3 years of age, which, just to give people a frame of reference, we get mice 2 years of age, and they usually die within a week after we receive them of age. So these mice are really literally like about to die. And we don't see very drastic changes in their skin mechanics. And it's very disappointing because, we wrote an entire grant around that. And in our naivete, we're like, I mean, these mice are super old, right? They're like 70 years or 80 years equivalent human age. but it's just apparently not a very good model for, mouse or skin aging. And I wonder whether that translates to other collagenous tissues as well. And I just wanted to hear your thoughts on, and maybe for everybody's education, how do you pick a mouse or like an animal model? And when do you say it's just a bad model? Not suggesting that yours is. In our case, I think it may just be a bad model.
Oh, believe me, that's why we started this whole aging study, which I don't have time to present here. But so two things. I guess our interest in aging started off with what happens to these mice when they're exposed to cigarette smoke, or better, thinking about this idea of the dialogue between, or communication in a sense, between cardiovascular disease or any disease with the aging process. Can we interpret the finding of the effect of smoking as an accelerated aging process or not? And of course, in order to do that, you kind of need to study the process of aging into in your model. We started using wild type instead of ApoE because I didn't want it to have confounding factors of the gene mutation, but of course, we're going to have to do that too. And so I think from a cardiovascular mechanics perspective, we like to think the many features of the cardiovascular system are preserved across species. And so we say, circumferential stress is similar across species because we have both the loads that are similar, and then the ratio between inner radius and thickness are preserved. The reality is that, rodents and any other animal species are not humans, and they will never be, right? And so the mouse heart beats 10 times faster, and yet mice do not live long enough for the elastin to fully degrade. And then, under repeated loading cycle, not even after 2 years. And so I don't want to give a straight answer to the question, are mice a good model of vascular aging or not? I think that the fact that the elastin doesn't degrade is, of course, a huge difference. There has been some recent work by Catherine Zhang and a collaborator that I forgot the name at the moment, but they do see an increase in the proteolytic activity of the elastase. So perhaps, and that's something that I'm throwing out there and definitely needs to be looked at, but perhaps we don't see visually, we don't see any degrading elastic fibers by the 2 years of age. And this graph, shows pretty well what you have seen before, what you said before, that as soon as you get them, they start dying. But they may still be less competent from a mechanical perspective. And so kind of trying to dissociate these two concepts of being structurally intact and being fully mechanically competent. And the other thing is that we see an increase in the collagen deposition. And so if you think about how the stress are distributed, why do we have this increase in collagen deposition over the months, over the 2 years in the mouse, if the elastic fibers are not fragmented and we do not really see an increase in blood pressure? So does the collagen still, no matter what, even if the elastin is not fragmented, does the collagen still take up the load? And so you at the end have the same effect as you would see in human and seeing these structural stiffening of the artery. So I think there is a lot more to think about before completely saying, that they're not good models. I don't think I have a definite answer for that.
Yeah, I didn't necessarily expect you to have an answer. I was just, I think we're just a little shocked. We were really hoping to see these drastic changes, and we don't. So I thought it was interesting for you to have pointed that out similarly. Yeah, I really appreciate your insight.
I think some of what she was saying with the elastin degradation and the half-life of the protein could be what you're seeing also in the skin as well.
Yeah.
Yeah, we're starting to look into trying. So we started out somewhat naively with mice that were, I think, like a year old. And so, the reviewers immediately told us, don't call it aged. No, don't call it old, to call it aged. And so, we tested and we saw some minor differences. Interestingly, and I that's my favorite outcome of the study. The biggest difference we found was that they build up fat on their ventral side. Another way where these mice build little bellies, but only on their ventral side. But outside of that, we didn't see much mechanical changes. And then we went to these old mice, which are a pain in the butt because, they arrive. Some of them don't survive the shipping, and then they get here and then they die within a couple of days. But even in them, and maybe my student Ella, who did the experiment, she's on this call, maybe she wants to chime in what changes, but it's very minor changes. We see the sort of the stress strain behavior kind of shifting to the right, meaning they become sort of more pliable, right? But the stiffness actually doesn't change very much. But yeah, nothing drastic.
Yeah.
I think there might have been a couple more. I think I saw some person raise their hand and then take it down immediately, and then a video came on and came off. So there might be a couple of questions out there. Maybe we could get to those.
Yeah. Hello. So I had a question. So it is known that cigarette smoke causes damage, and you mentioned that e-cigarette is the new thing that has to be researched. So is there a plan to create a chamber as you shown, but instead of cigarettes, it would be e-cigarettes being used into a chamber like that, and seeing a study like this done on what's actually happening to this valve?
Yes, we have finished that study. And Yasmin and Hector are currently analyzing the data for the electronic cigarettes. One of the, I would say, disadvantages of the electronic cigarettes is, or one of the challenges is that, they were introduced in 2006 and we are already at the 5th generation. So when Jessica and I started this project, we actually thought that we would study the tank style electronic cigarettes. And then by the time we were ready to actually do it, and COVID, of course, occurred, and I kind of set up, caused further delays, we realized that was not relevant anymore. And so we moved on to Juuls, which are these pot style cigarettes. And there are some very scary data about the use of those things between or amongst adolescents. I think that the most recent report says that 20% of high school students reports a daily use of Juuls, at least in 20 out of the 30 previous days. So based on that relevance, we kind of studied that. We haven't finalized it, and that's why partially why I did not present anything here. But based on what I've seen, I do not think that we can say that they are safe. But just stay tuned, and hopefully 6 months or so, we're gonna have the answer.
Okay. All right. Thank you.
One comment that I have, Chiara, I really appreciate about your work that it's very clear that you took tools that you had learned in your previous training and then applied them to a problem that's very different from what you've done in your training, and also has such importance and currency to a societal problem. I really love that about this project, and part of, I think, why we selected that paper. I think it's a really nice example for how you can leverage past experience to do something novel and innovative. And I think it's hard. Anybody who's gone through this process of disconnecting yourself from your previous advisors has experienced how tough that is. And I think you have done that really nicely.
Thank you. It always, like the part that I mostly presented here, in a sense, like the characterization of the arteries and the microstructure, that was something that I've done before, that I was comfortable with, and I was comfortable in training students. And of course, there is always that experimental anxiety of like not breaking a vessel from a mouse that has been treated daily for 6 to 8 months, but Yasmin did a great job with that. I do think that the most challenging part from my perspective was really the development of the exposure framework, because I had not much experience. And so trying really to build up a model that could be consistent, I think that was really the most challenging and the most time-consuming part. And of course, you start by reading the literature, and then you start plotting things and results, and there's no trend, and that's because there are no standards. And so I do think that, like in everything, we should really try and push to make standards.
All right. Any other questions out there in the world? Just real quick, in the last few minutes that we have, I do have a couple of questions. So one, if you could comment on why in the study you only focused on female mice specifically. You know, a lot of times now, certainly as you write grants and papers and things, sex as a variable is an important aspect of many studies. So if you could comment on that just really quick in the last few minutes, I think that might be to have some of your insight might be helpful for.
Yeah, absolutely. Like you said, sex is a fundamental biological variable, and we do plan, or we planned on comparing the long-term effects of environmental pollutant in both males and female. And you know, we have other projects where we have used males for a different exposure, but it's still biomass, and we do see differences. And so I think it's warrant doing it. We're probably very naive at the beginning, thinking that we could do everything. And so we started off with female. So why did we start off with female? I think that's kind of a something that I can try to explain. So there is some epidemiological evidence that shows that exposure to cigarette smoke has greater impact on lung function of females than males. And then interestingly, more female than males are admitted to the hospital with COPD, chronic obstructive pulmonary disease, than male when they smoke. There are sex differences in peripheral arterial disease and myocardial infarction with smoking. And then looking at the ApoE mice, they seem to develop female larger and more advanced lesions. And so that's why we decided, and they are an understudied population, I should also say that. So that's why we decided to start off with females, but it is essential to repeat the study with males.
I think also, you know, when you think of smoking, I think, you know, basically what you're having is sort of the systemic inflammation that's happening, right? You have inhalation in the lungs that leads to some immune activation that has many of these downstream effects. And we know now that the immune system in females is different than the immune system in males. And there may be evolutionary reasons for that and many reasons for that. So I think you're right. Certainly in this context, looking at males and females will be important, but studying sex as a biological variable will be very important moving forward. So.
Yes, absolutely. All
right. Well, any other last minute questions? I think we are pushing it right to the end, but this is good. All right. Well, if not, maybe we can, I will thank the speaker again. Chiara, you did great. Just to kind of echo what Manuel said, I think this is a really cool problem that's timely and pressing, you know, and it's inherently a human condition, and it's very interesting. So it's cool to see it all coming together.
Well, thank you, and thanks to everybody who attended and everybody who organized it. It was fun.
All right.
Thank you, Chiara. This was amazing.
Thank you.
Really appreciate
Thank
it.
you very much.
Thank you. I'm learning a lot here.
Great talk. Thanks.
And I also never start smoking, so that you did a great job too.
Just want to say, according to my mother, 1 cigarette a day is fine.
Manu, no, you're still recording.
Manuel edits the recording, so it's up to him whether or not he keeps that in.
That's true. We're in the end of it. This is all getting cut anyway.
I'll stop it.